now we look at a general system. So for rotation, we're not going to look at a bunch of just particles moving around. Because you cannot define rotation if they're just moving randomly. Like, is the system rotating clockwise or counterclockwise? It's not defined. There's no such thing as rotation. So we're not looking at this type of system. We're looking at the system that all the particles are rotating together. So it means that you might be looking at something like this. Here's the pivot that you're going to rotate. There's a particle this far. There's another particle this far. And there's a lot of other particles. All might be located at different distance from this chalkboard study. Yeah. Anyway, when you're looking at a system that is rotating together, what you mean is that if M1 rotates by 1 degree, M2, M3, M4, all the way to Mn all need to rotate by 1 degree. You are not looking at a bunch of particles moving randomly. You are looking at a thing that has a lot of particles, and when it rotates, the shape doesn't change. Otherwise, you can't really define rotation. Okay? So, in this case, what we're interested in is how to compute the moment of inertia. For a particle, it is easy to just multiply the mass with radius squared, and then you get moment of inertia. But like here, there's a lot of mass and a lot of distance. You don't know what to do. To get that, we again use energy conservation. Okay. Let's look at a torque. It doesn't need to act on any of those particles. Let's say there's a rod with distance r, and then you apply a force F. Again, it is always perpendicular to the lever arm, so the torque caused by this force is constant. We don't know how big the moment of inertia for this system is, but we can write it as torque equals I alpha. So in terms of torque and moment of inertia, what will the angular acceleration of this object be? If torque equals I alpha, what will alpha? If F equals ma, A will be force divided by mass. Good, but you can just say torque divided by R. But yeah, that will be true in this case. In general case, it's just torque. For this case, I want to just see the moment of inertia of this object, so I make my life really easy by setting the torque to be a constant torque. Okay? Now, what I want to do is to rotate the thing by an angle. If I rotate the thing by an angle, I am going to move along the rod. I'm going to apply this force along the motion of the rod by a distance d, and I'm going to do a work which is force times displacement, and in this case, the radius is r, the change of angle is delta theta. So what will this displacement be in terms of r and the change of angle? This is r, this distance r. The angle is rotated by delta theta. So what will this distance be? R delta theta, good. It is again the arc length of this slice of pizza. Okay. Now, just like the linear motion, you can derive the relation between work and kinetic energy by using the relation between change of velocity squared and the distance you accelerate. Let me review what you have done for your homework. You showed that if I define x velocity to be the change of x position per time, and x acceleration to be the change of x velocity per time, then you get that for a constant x acceleration, you get that for constant x acceleration, the change of x velocity squared will be 2 times x acceleration times the x displacement. Do you guys remember that? Do I need to prove it again? Alright, so similarly, we define angular velocity to be the change of angle. If you look carefully, you can see I'm just selecting all the x and replace it with theta, selecting all of the x, replacing it with omega, and select all the ax and replace it with alpha. Because their relation is exactly the same, so if I have a constant torque, which gives me a constant angular acceleration, I will get that the change of angular velocity squared equals what?
2 alpha delta theta.
Good. Good. Okay. So that's how you can apply the math you already done to new stuff. Okay. So here, after we apply a change of delta theta, we can replace it by a change of omega squared divided by 2 alpha. So I'm going to do that. Okay. Now, what's the relation between this radius and the speed and angular velocity? I'm sorry, not yet. That's all right. So this is true, okay? And what energy conservation tells us is that this work will turn into what kind of energy of the system?
Kinetic energy?
Good job, kinetic energy. So after you input this work, the kinetic energy will increase. And let's say you rotate it from rest. So the kinetic energy will increase by 1/2 their mass times their speed squared. And you just add the energy for all the particles. I am rotating from rest, so that I'm letting the initial kinetic energy to be 0. So after you input the work, the kinetic energy will change by this. Okay? So the speed is the speed of individual particle. If the particle is closer to the center, the speed will be slower. If it is far away, the speed will be faster when you are rotating together. What is the relation between V1, R1, and omega? What's the relation between speed, distance, and angular velocity?
So they each go up together.
Yeah, and the exact relation is, what is the relation between speed, radius, and angular velocity?
V equals radius times angular velocity.
Good. V equals R omega. So you can replace the V here with their individual radius, and omega is the same for the entire system. It is V squared, so you need to square both of them. Okay? Same for the second particle, but the radius of the second particle is different than the first particle, all the way to the particle. Okay? So if you look at this, you see they all have 1/2. They all have omega squared. So you can take them out. And what you need to add is just the mass of the individual particle times their distance to the pivot squared. I should give you more space here. So you see, even though they are rotating together, the speed is different, so we cannot just say the energy is 1/2 total mass times center of mass velocity squared. But the angular velocity is the same. So we can express the kinetic energy with the same angular velocity. But to do that, you need to convert everything into mass times distance squared. So let's look at here and here. The work we done should increase the